Hello and welcome to Wirefryer. I would like to begin this video with a question. Have you ever seen a display like this before? I would honestly be surprised if you haven't, because it is found in many common household items like stoves, microwaves, and alarm clocks. Displays like these are really interesting when you take a closer look, because although the numbers look basic and rigid, this design is super popular today because of its simplicity. More on that later. And this masterpiece of the game is called Yeeps Hide and Seek. The concept is simple. The game started with a stuffed animal puppet monster called Yeep, and your goal is to find and chase down other Yeeps and tickle them with red pointy things, while having the ability to build and use gadgets to widen the variety of gameplay. What makes this game so important to the subject of this video is the game receives constant updates from the developers, and the developers use ideas from the community to improve their game. For example, in the time that I've been making this video, they added cooking, potion brewing, and pets. There is a whole lot more to this game, and I think what truly makes this game great is how there's something for everyone, whether it's trying to outmaneuver others with speed and agility, duking it out in the free-for-all arena, tinkering and building with the many blocks, or just hanging out with the community with the gadgets. But this is not why I'm here today. I'm here about a completely different feature. And of course, I'm talking about the best set of blocks in the entirety of the game. In my completely unbiased opinion, the logic gates. So of course, I did the first thing any logical person would do, and spent the next 5 months of my life designing and planning an entire addition calculator, wasting tens of pages of notebook paper, and Googling. A lot of Googling. But then it hit me. I had never attempted such an ambitious project and needed to split it up into 3 separate parts. And this video is going to be focused on the first one, being the displays. So I think the next logical step to making this video is talking about how they work. So as I mentioned at the beginning of the video, these displays are commonly found in the real world, and they're called 7-segment displays because they use 7 segments or lights, either being on or off, to make any number 0 through 9. This means that if you had an infinite number of them strung together in a row, you could make any number. The reason these displays are so often used is because instead of having modern screens with millions of pixels or tiny lights, these displays technically only have 7, conserving power and making them easy to use. So to make the display in Yeeps, in my final design I used 1x1 lights for the segments and filled in the rest with wood painted black. But if you do not own the lights, I also made a simple wire design where the lit up wires would represent each segment. Now the first problem for making these displays occurs when we try to make numbers. You could just manually activate each light, but it's a difficult task and not super reliable. So now we need a way to send the numbers to the displays, but we only have wires that can either be on or off. If we though think about a wire being on as a 1 and off as 0, we can use a different number system as our input. Hence taking us to our next section, counting in binary. Binary works great with the Yeeps wiring system because binary numbers can be made up of only 1s and 0s, making it work perfectly for our scenario because the on wires represent 1s and the off wires represent 0s. Let me quickly explain how to count in binary. So let's begin with what you already know, the decimal counting system, also known as base 10. As you know, when you count in base 10, once you reach the number 9, you add 1 to the next digit and set the first digit to 0, making it 10. Keep this in mind. Now let's do side by side of counting in base 10 on the left and binary on the right. 0 and 1 are identical on each side because you start with 0 and add 1 to each. 2 is when things begin to get interesting though, because remember how I said once you reach 9 in decimal and you add 1 to the next digit and reset the first one? In binary, it works the same way except it happens every time you reach the number 2. Because we cannot have 2, we add 1 to the next digit and set the first digit to 0, making 2 in binary 1, 0. Now for the 3, we add 1 to each side, so base 10 becomes a 3, and in binary though, when we add 1 to the number, it becomes 1, 1. For 4, we add 1 more to each side. In decimal, it becomes 4, and in binary, we need to add 1 to the first digit, making it a 2. But because there cannot be in 2 binary, we add 1 to the next digit and reset the first digit to 0. But again, we have another 2, so we add 1 more to the next digit and set the second digit back to 0. So in binary, 4 is 1, 0, 0. We can just repeat this for the next numbers. So for 5, we add 1 in binary, making the number 1, 0, 1. 6, again, we add 1 to the first digit, which then becomes a 2, so we can carry the 1 to the next digit and set the first to 0, making 6, 1, 1, 0. For 7, we just add 1, making the number 111. No carrying over needed. And 8 is probably the hardest one here, if you understand the process. We have to add 1 to the first digit, which makes the first digit 2. Then, as you know, we add 1 to the next digit, set the first digit to 0. Then again, because we have a 2 in the second digit, we add 1 to the third spot and set the second digit to 0. And finally, repeat one more time and adding 1 to the fourth digit and setting the third digit to 0, making 8, 1, 0, 0, 0. That is the hardest one we have because finally, we add 1 more to make the number 9, 1, 0, 0, 1. Because our display here can only show numbers 0 through 9, we don't have to count any higher. But if you were to count higher, you can just repeat for larger numbers. So here back in game, we can represent this binary input by using toggles and buttons. To make the binary number 1 by pressing this button, or 9 by mixing these two together. Can't see that. So now that we have our input and our display, we just need all the wiring in between. Now, you could technically use anything for these inputs, as long as you do the next step with your inputs, and that you have enough inputs to match each of the 10 numbers. Now, this is what I believe to be the most important step, and that is to make a table called a truth table. I actually learned about these in school, but never thought there would be an actual use for them. But I was very wrong. I apologize that I can't go into a lot of detail about these truth tables, or else the video would be a lot longer. But I will explain them the best I can. And there are a lot of great videos online about these truth tables, or anything else I'm teaching about here. If you have any interest in learning about them further, I would definitely recommend watching further videos. But to begin with these truth tables, right now we are looking at a finished truth table for segment A. And as you can see on the right, the top segment of the display is segment A. You can do this, you have to do this for one segment at a time, so I just decided to start on A. On the left, you can see the number in a number and the binary equivalent of that number. And on the right of the table, you can see what we want our segment A to display when we give it a number. For example, on the right in the diagram, you can see that for the number 1, we want our segment A to be off, while B and C are on. So under the A output column at the 1 position, we have a 0 there, showing that display will be off. As you continue through each of the 10 different numbers, you would write the corresponding state of segment A for each of those numbers. So the final step in the logic for these displays is figuring out what logic gates you'll need to activate each segment correctly. I'm going to again be working with only segment A and showing the truth table for the segment A in the bottom right. So basically what I'm making is a math equation where each digit for the binary number is the input. Let me show an example that it makes sense. So starting off, as you can see, beautifully drawn in the right, it shows that when two variables are being added, it means that there will be an OR gate between them from Yeeps. And if they're being multiplied, it would use an AND gate. Also, if there's a horizontal line above a letter, it means that there's a NOT gate before it. So what you do is you look at every place where a 0 is shown in the output of segment A. Then you have to look at the binary for that segment and for the input of that segment and all of the inputs for the binary and set them all to 0 using NOT gates. For the number 1, the binary number shows 001 and the output of segment A is 0. That means that in our equation, if we replace each of the binary inputs with letters A through D, one for the 0, 0, 0, and 1, then put OR gates between them and invert the D because it's a 1, so it'll set to 0, and we repeat that same process for number 4 and put AND gates in between them, then the final step, then you have the final equation. All you have to do left is simplify. And if you've taken algebra, you know what I mean, except this simplification needs different properties and things because it's Boolean algebra and not just normal algebra. And I've honestly tried to simplify these. And I've simplified them a lot, but I found this website that did it much, much better than I did. And it simplified it to a very simple answer. Also, there is a way to do it where if there are less ones, so that you only have to work with the ones, but that requires a different equation. If all that went completely over your head, out the window, down the street, into another country, I do not blame you at all. Because I really struggled with making this semi-beginner friendly while still having the information. I should honestly put a math warning at the beginning of this section. So I feel it's important to reiterate that if you want to learn this stuff, I really encourage you to watch another content creator's video, because they would explain it much better than I did. Also, if you don't want to put yourself through the stress, here are the homework answers. So now finally, with all of this complete, all that is left is for me to, build the display. So that calls for a 1-minute build montage. And while this is running in the background, I want to talk about all the ways displays like this could be used. Because although I'm making a calculator, you could use these displays in, let's say, to keep score of a competitive game where there's two teams against each other. Or make a visible game timer where the timer counts down. A high score for a game, the implications are countless. And I know that this video was not a full build tutorial, but I plan to make a full tutorial with examples after I finish the calculator. Also, little may some know, but these logic gates are actually useful in real life because computers, or whatever device you're watching this video on, uses billions of logic gates inside of it. And now, I think it's finally time to show you the display. So after all of that, here is my final in-game displays. They are fully functional, surprisingly, and I guess I showed you. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8, and finally 9. So, 0 through 9 on a Yeeps 7 segment display. Before I end this video, I have one last thing to say. The reason I have 2 displays is because I already started planning for my next video, a 2-digit display. This is one step closer to a fully functional addition calculator. So if you watched this far in the video, I would like to thank you, and remind you to keep learning.